Now, with the big black holes, what we call supermassive black holes, that are, so the little black holes, like, you know, only the mass of the sun, are like scattered around our galaxy. They're the endpoints of stars, of big stars. But the supermassive black holes, there's like one per galaxy, caveat usually, and they're, instead of being the mass of our sun, they're 1 million to 1 billion times the mass of our sun, and they're correspondingly bigger. The event horizon of the black hole, the size of the black hole, instead of being a mile across, is the size of the Earth's orbit around the sun, like 100 million miles across. But what that means is that the gravity isn't changing so quickly. It just scales up. And so the gravity, you don't get spaghettified until you're already well within the black hole event horizon, and it's way too late to write home. And so you can actually survive falling through the event horizon and experiencing it. And so that's the cool thing about supermassive black holes, is you could get quite close to them without dying. But then after a certain point, you're through the event horizon and you're going to die, because it'll take you a few hours to hit the center. But the thing about a black hole, so the other thing you want to know about black holes, quasars are basically black holes with a lot of bad stuff happening around them, right? As you go into the black hole, the geometry changes. Euclid no longer applies. Left and right start going behind you. The amount of direction into the black hole becomes more than the amount of directions out, until you pass through the horizon. Every which way you turn is in. And that's why you can't get out of the black hole, is that there is no way out, literally. And it's actually literally in the math that space becomes like time. The normal difference between space and time is that in space, I can go forward, I can go back. In time, I can get to tomorrow, but I can't get to yesterday, sadly. And so absent a TARDIS, I'm stuck in that one direction in time. And the inside of a black hole is exactly that, mathematically. It's that your direction into the black hole has become the future. And so there's a bunch of other cool things about that, but it doesn't matter, because if you get into the black hole, you're not coming out. So you can't test that. But outside the black hole, you can get back, light can get out. And so we can study the regions near the black hole in actually quite some detail. And so that's what we do. That's why we're interested in quasars, because it tests the laws of physics, which are the rules of the game that we live by every day on this world. And it kind of tests them to breaking point, right? It puts them in a really extreme situation, and we can watch nature do that experiment and get a better understanding of the laws of physics.
Okay. Is there any interest in looking into that more efficient method of transferring matter into energy as something we could reproduce?
Yeah, the only snag with it is it requires a
black hole generator,
and preferably millions of times the mass of the sun. So it's not something you really have in your living room. So I don't see any way that that can be parlayed into something for use on Earth,
right? Or even in the galaxy somewhere, right?
Yeah, I mean, a super advanced civilization might be playing with stars and smashing them together or something to do this. Yes, that you could imagine that. I think we're ways off. I wouldn't
quite a ways, yeah.
Just yet.
Right. Let's get good at leaving the solar system first.
Yeah, right.
Traveling around with it.
Yeah, this is something where the environmental impact assessment for a machine that can destroy whole galaxies is like, not in my backyard.
Right. Do it over there. All right. Well, let's come back then to from those grandiose ideas to something simple, the International Space Station. It's being considered for commercial ventures. You've had some ideas to talk about that. What's your opinion on that? Can the ISS even physically handle this kind of change?
Oh, I mean, physically, yes. You could. If you had the money, you could do some useful commercial stuff on the ISS. What I don't see any way you can make a profit doing that, right? I mean, the ISS is incredibly expensive to run, and the commercial experiments that are being done today on the ISS are getting a lot of that benefit for free. They're not being charged for the cargo ships, the astronauts, the maintenance, and all of that. And so I think if NASA, and so the problem is this, that we have the ISS, but NASA wants to spend its budget on moon missions. And if it's going to spend its budget on moon missions, it can't afford to keep running the ISS. And so it's desperately looking for someone else to pay for it. But I just don't see it. I mean, I think the amount of money that it would take to operate the ISS commercially is just insane from a commercial point of view. And the profits you could imagine making from microgravity experiments don't come within orders of magnitude of justifying that. Now, that's not to say that one couldn't have a profitable LEO space station for commercial purposes if you architected it differently, but it would have to be a lot more bare bones, designed with cost efficiency in mind from day one. You know, it's not clear yet if that'll happen, but that's more likely than having the ISS be self-sustaining commercial.
More engineers are not going to solve your problem. It's not a technical problem in that sense. It's a process problem. And the time to fix your processes was 20 months ago, and the second best time is today. This is Jason Kanigan, the president of Cold Star Technologies and the host of this podcast, the Cold Star Project, which is all about identifying and solving process problems for space companies, because that's what we do. And you can hear the entirety of this episode by following the link in the comment below.